you didn't fly away with this wind. Can you hear me well over Zoom?
Yes, perfect.
Okay, thank you. So the idea for today is to give you a super quick overview on additional tools and more advanced techniques that we developed to do performance analysis. And yesterday, you got familiarized. This is not. One second. One sec. No, anyway. You got familiarized with the main core tools, especially Extrae and Paraver, and I'm pretty sure you started to get this feeling when you were working with Paraver that you start to open windows like timelines with the IPC or the instructions or the useful duration or cache misses, and then you looked at tables, you look at histograms, and soon enough your screen was crowded with small little windows full of colors, which look similar, but then the colors mean different things depending on the window that you're looking at. And this, especially at the beginning, can become a bit daunting and confusing very quickly. So the idea is, can we apply techniques that automatically process the data and give us insight? And so we have been leveraging techniques from other fields like signal processing, image processing, data science, to do just that, to process the trace and provide us with insight, with complementary views that help us understand the performance and the behavior of the applications. So today I will give you a quick glimpse on 5 of these techniques. The first one is obviously the basic analysis. This is a script that processes the trace, computes different metrics, provides the pop efficiency metrics, and I will say no more because Sandra will give us a more in-depth introduction to this tool with a hands-on to try it. But I wanted to give a quick tip because we have been speaking about you can apply this to a single trace to get the efficiencies. Good. If we want to get the computational scalability metrics, we can apply to 2 or more traces. So we have one baseline to compare with, and this is useful to do scalability studies. But taking advantage of the flexibility of the tools of Paraver that allows to manipulate the trace and select sub-regions of interests, what we can do also is to do cuts of the traces at different time intervals, for example, or at different iterations, and then apply the basic analysis to different phases in the same code over time, okay, to compare them. The next technique I wanted to show you is based on clustering, okay? The clustering in the common sense of the word, or to make groups of things that look similar. And what we do here is, for example, we have one timeline with instructions, one timeline with IPC. What we have here is computing phases, okay? And here you can already identify some sort of a structure, right? You can see that here it looks like there are 2 iterations, okay, that start with a large blue phase, and then these phases over here, and then the pattern repeats. Okay, when you look at the IPC, it's not so clear because all the colors are a bit more bluish, but you can still see something. So what we can do is to, for every computation that we have on these timelines, draw a 2D plot like this, where we put across for every computation with respect to the number of instructions executed and the speed at which these instructions have been executed. And in most cases, we get this kind of drawing with dense clouds, on top of which we can run a clustering algorithm, which in our case is a density-based clustering, that identifies these groups. And this can explain us characteristics and structure of our application. This is telling there are 1, 2, 3, 4, 5, 6, 7 different phases, regions in the code with different performance behavior. And here we can see that, for example, the red cluster, which is the one on the top, is the region that is doing most work, highest number of instructions, followed by the purple, for example. Then we can see that the yellow region is the one most on the right. So this one is the one that executes with highest IPC, faster speed. If you remember yesterday, we were saying that what we When we look at a histogram, we like to see straight vertical lines, which means that all processes are presenting the same behavior. So in this case, what we like to see is compact clusters, which means that they have little variability. And what we don't like to see is this kind of elongated clusters, dispersed clusters, because this is telling the computations that fall on this corner are the ones doing more work because they are on the top, and they are going slower because they are on the left. Whereas the computations that fall on this other corner are the ones that are doing less work and it's done faster. Okay, so the situation here is the one that has more work does it faster, the one that has less work does it slower, and this is the worst situation of all. Then, depending on how this happens over time, this will be unbalanced or not, because it could happen that at some point in time, we are all working slowly. And then later on, we are all working fast. This is not ideal because we would ideally want to be working fast all the time. But there is a worse situation in which at the same moment in time, some of us are slow and some of us are fast. And if we have to communicate, this will be paid as overhead in MPI because ones have to wait for the others. Okay, but to know this, we have to look into the timeline, and then the clustering information is fed back into the timeline so we can see the distribution of clusters over time. And here you can see that what we thought are two iterations, well, they look like two iterations, but these two initial phases are different, okay? Because the red cluster and the purple cluster have different characteristics. One have more work than the other one and faster speed than the other one. So in combination with these two plots, you can give a quick overview of what is the behavior of the application. And this is not a rule of thumb, it's a super huge oversimplification, but in general, if you have things on the top right, that is great because you're doing a lot of work fast. If you have things on the bottom, well, this is okay. It's better to be on the right than on the left, but in any case, it's little work. And in general, what you don't want to have is things on the top left. Okay, this means a lot of work done slowly. So things that fall over this corner can be initial targets for optimization. Then, as you will see, all our tools interact with each other. So we can combine the clustering with Paraver and with the timelines and with the histograms. And so you can correlate the information. So in this example over here, you can see there are these four phases that are the ones that do more work because they are on the top. And they seem to go in pairs because yellow and dark green are on the same horizontal line, as well as light green and red, which are on the same horizontal, which means that they do the same number of instructions. Okay? In the timeline, you can see the distribution of clusters over time, and you can see that some of them happen simultaneously. So at the same time, we have yellow and dark green, which have very different behavior. So they do the same number of instructions, but at very different speeds. So, and this is happening at the same time. So this will generate an imbalance. Okay, same for these two. Light green and red are over there, and they happen at the same time. And this will generate an imbalance. And you can check that in, for example, this is a histogram of the duration of the computations. You can see that the one that takes the longest is the yellow cluster, while the light green and the dark green, they take the same amount of time. Okay, they take the same amount of time, but they have different characteristics, different amount of work and different speeds. And this is a histogram of the number of instructions. And you can see that at the level of instructions, the light green and the red, they have the exact same amount of instructions. So you can correlate all this information combining the tools. And we can also use the clustering with MMS. And this is a what-if simulation. What would happen? Well, I have an execution with these two clusters. The scatter plot looks like this. The yellow cluster is faster than the green one. There is huge dispersion in both of them. So what would happen if we were able to speed up the green cluster, which would mean that we move it to the right to be as fast as the other one? So with MMS, you can simulate this, and it will tell you you would gain 13% of the execution time. We could also simulate what happens if we are able to eliminate the dispersion of these clusters. If we were able to do that, we would gain a 19%. What DMMAS doesn't tell you is how difficult it is to achieve this. It only tells you if it is worth putting the effort in doing that. The next tool is tracking, and tracking is useful to compare different clusterings. Here we are looking at 6 different executions of OpenMX at different scales, from 64 ranks to 512. Because clustering is an unsupervised algorithm that depends on the data, and these are different executions. Every time you do the clustering, you can get different clusters, different amount of clusters with different colors assigned. And so when you compare the clusterings between them, between 64 and 128, it's still quite easy to identify who is who, but as you keep increasing the scale, the variability increases, and then there's more clusters appearing, and then if you try to compare 64 directly with 512, it's not that easy to explain who is who. So what the tracking does is just that, to play who is who and identify which regions, which clusters are the same along the whole sequence of experiments, and then redraw all the clusters to assign the same colors. And now it's much more easy to compare, right? So when we have this, we can condense all the plots into a single one where the clusters are identified by their centroids, and then we draw trajectory lines that express how these clusters, regions of code, are evolving in performance regarding instructions and IPC through the sequence of experiments. And here, what we are seeing is that there are 3 clusters that go down. And this was expected because this was a strong scaling test. So we increase the number of processes, we reduce the number of instructions per process proportional, and that's why they go down. But then what we see is that there are 3 that are not moving. So these regions of code had a problem of code replication. And so with tracking, you can evaluate any parameter that makes sense for the performance of your application. You can change it and then apply tracking over a sequence of experiments to see how the different regions of code evolve in performance. Then folding is like taking a microscope and then looking at one single instance of computation that fell on one of these clusters, and then looking into that one with high level of detail. And the idea of folding is, imagine we have this situation where one process is doing MPI and computation over several iterations. By default, Xtry collects information at the instrumentation points, at the entry and exit time of MPI, which are these yellow arrows. So if we want to look what happened into a single computing phase, the information that we have is a measurement at the end of the previous MPI and at the beginning of the next one. And so we can compute the delta between the measurements, and we have the duration of this phase. So what we can say is that, okay, in this phase, which is about 600 milliseconds, we have seen 2000 MIPS. So is this uniform over the whole phase? This is an average, but the real behavior has been uniform? Or maybe an even more important question, is it good enough? But it is not so easy to say that just by the numbers. So maybe a more important question is this easy to improve? And then there's where the folding comes in. The idea is to combine instrumentation with sampling. Now, if we had a sample in the middle, we could measure if we have half of the measurements at half of the computing region. And we could say if these 2000 MIPS in reality have 2 different phases. But one sample is not enough. So what we can do is to get more samples. But in order not to have a lot of overhead, if we use a low frequency, the samples will fall over different iterations. So what we do is to project these samples, to fold them all into a single iteration. And we do that throughout the whole execution, with all the samples throughout the whole executions. We combine them, all of them, into a single iteration, so it is highly populated with samples. And this allows us to draw that in reality, this average of 2000 MIPS behave like this, that it starts high at 3000, then it goes down, then it goes up again. So back to the question, is it good? Is it easy to improve? Well, this region over here, the performance is close to 0. So this is so bad that it should be easy to improve, right? So with folding, we can combine with CPI stack models. And in this example, what we saw was when the MIPS go down, in the CPI stack model, we see an increase on the LSU basic latency, which this is indicating problems in access to memory. So the tool is able to pinpoint exactly to the line of the code where this is happening. And we went and checked the code, and there what we found was that there was a nested loop traversing a matrix by columns instead of by rows. Okay, and this was not taking advantage of data locality. Every access was a miss, and then we were waiting for memory all the time. So we just swapped the two forks in the nested loop, which is a trivial fix. Then the access is by rows, and then what happened? That the green disappeared and the computation shortened by 30%. Okay, and we were able to do that because we had this microscope that pointed exactly to one line in the code. And then the last thing I wanted to show you today is that lately we have been incorporating also models for the memory behavior. And here we are looking at MES. Okay, MES characterizes the performance of the memory with these bandwidth latency curves. Okay, so here what we have is bandwidth, this is latency, then the different series in this plot are ratios of read versus load operations, so that the black line on the bottom is when you are only doing loads, and the black line on the top is when you are only doing writes. And then all the intermediate ones are different ratios of read versus writes. Okay, and the dots in the plot are segments of the execution. Okay, we take samples at, for example, 10 milliseconds. So every 10 milliseconds of the execution is one of these dots. Depending the amount of reads and the writes and the bandwidth that is being consumed, we put a dot in here, and this tells us what is the latency of the memory. How much do we have to wait for that data? And then with all these metrics, they devised a new metric, which is this stress score, okay, which is just a number that tells you how saturated is the memory. Then integrating that with Paraver, we get to see this stress score over time. So we get to see that at these points over here, okay, it's a bit difficult to see, but this is a red that repeats over here and over there and over there. And we can see that there is a peak in stress at these points, Okay, we can correlate that with what the application was doing with all the other information that we have in the trace. We have the MPI calls, the call sites, so we can pinpoint back this behavior to where it happens in the code to better understand what is the impact and the influence of the memory. So that was it. It was a sneak peek of these other techniques. All of these together with the core tools that we saw yesterday conform this BSC tools ecosystem, where the trace is the central unit of exchange of information. The trace is the input for all of these tools, and in many cases the output of these tools, because they provide back a trace with enriched information, like, for example, the clusters information or the microscopic details of the folding, together with complementary views like the scatter plots of the clusterings or the trajectory lines of the tracking, or these models like the CPI stack or the memory models that help us understand better what is going on with the applications. So that was it on my side. For the remaining of the session, we had 3 more things. One is a hands-on on using the clustering to do analysis, but this one we are going to leave it for the end, to see if we have time, just to leave room for the other 2 things. In case we don't have time, you have it on the slides. It's super straightforward, and we can help you afterwards to follow it if you need, or if we don't have time to do it together. And then the 2 other hands-ons that we prepared are, on one side, a more in-depth presentation of the basic analysis tool and how to use it to analyze different cases of MPI applications, hybrid MPI plus OpenMP, and MPI plus CUDA. and then also a hands-on on how to get a CUDA trace and analyze it with Paraver. So with that, I give you in good hands. So Sandra, please.
We'll start with the basic analysis. Yeah, this is our tools to obtain the pop metrics. First of all, I will start with the workflow of the basic analysis to understand how this works. And we can see that we work with the extract Paraver traces. So we use Paramedir. Paramedir is a utility from the Paraver package, and we take traces, the original traces, and also when we are working with MPI traces, we simulate these traces and obtain the simulated traces and analyze the two to obtain by using a different configuration file that is related with the Paraver uses, and we obtain the raw data related with the trace and the ideal raw data. By using this information, we compute the metric and obtain the pop metric. A basic analysis detects automatically if you are working with MPI only or if you are not using only OpenMP or you are using combination of MP with OpenMP or with CUDA. Yeah, so this is the word that we have here. So this means that we have dependency. Yeah, we have dependency with Paramedir. That is a mandatory, so we need Paramedir in our system to use basic analysis. And also we need DMMAS, but DMMAS is optional. But this means that we don't have DMMAS in our system, we can obtain some submetrics related with the communication. And basic analysis don't need a special step to installation. You only need to download the package and put in your path. Remember to add the path for the requirement, and the use is easy. Really, we only need to put the model factor.py, that is the script that processes the traces, and we need to put the list of traces. Yeah, this is not difficult. You can obtain basic analysis from our white page, or in our case, we also can use in Mare Nostrum 5. We provide basic analysis through the VIA modules. Is you only need to see the availability or you load the basic analysis. Basic analysis, when you will load the basic analysis, we load all the dependency. Yeah, so if you need to change some, you need to download and load again the version that you want. And to see the different parameters that we provide, we have a health associated. And as we can see here, we only need the model factor.py and put the path to our trace. And in the case of the MPI plus CUDA, we need, in that case, to select the model that we use to compute the traces. Yeah, so you can test this in the system, but the idea now, I will try to advance with the presentation related with the different case that we have here. When we will start, I know this is the ruleless cases that I suppose that all of you test yesterday, yeah, in the hands-ons. So we reanalyze basic analysis for 3 traces. Usually we use basic analysis when we have several traces, so we can see the scalability behavior also. And in that case of ruleless, this is the run in Mare Nostrum in the ACC partition. And we have the iteration here, and this is a weak scaling cases. Yeah, so now we only need to apply basic analysis to obtain the pop metrics. This is, I remember that Marta explained in the other day that we see value in our table. This is the output that we provide with basic analysis, where we have in the column the number of process and in the row the metric. This is an MPI application, so we see this kind of table. Remember the idea when we work with this kind of output, we need to see what happened with the red value that we put here with our color. So this is the idea to focus in that part, but also it's important to focus in the trends and the height value. And in that case, for these 3 cases, we have different cases here. For example, we can observe that the parallel efficiency is decreasing as we increase the number of processes, and we can see that the main factor here is the load balance. Yeah, the communication is more stable values for the 27, but this is for the mapping that we have here. And the other thing that we can see that really the transfer is perfect. Yeah, but this is depend also of the experiment that we have here. And the other value that we observe here is a log value that is related with the frequency. Yeah, in that case, this is related with the mapping that we use here. Yeah, this is the case for that we have a perfect mapping. We are putting, in the case of the 8, we are putting 2 processes per NUMA domain. Remember, this is done in ACC partition. This means we have 2 sockets and each socket have 2 NUMA domain. Yeah, so in the case of the 64, we are mapping 60 processes per NUMA domain. This means that the NUMA domain is near to fully utilized because each NUMA domain has 20 cores. Yeah, this is the architecture of the ACC partition. This is the reason that we have the frequency log value. Remember that this is in the case of the computation, we are also, this value is reference to this. This is the case reference. So this means that in that case, the frequency is low, but respect to the base case. Yeah, this is important to know because it's our base case has some behavior. Remember that in the scalability part, this part is related with the base case. The parallel efficiency, yeah, is individual for each running. Yeah. So we see the different behavior and we try, but when we work with this kind of table, the idea when we use this for assessment. Yeah, the idea when we work with this is to see what is the problem. Yeah, where we say, okay, here the thing that they are running that we have an explanation for the frequency. It's seen that the value is good, but we can observe that the parallel efficiency, the lower value is for the load balance. So we can focus there and see what is happening. Yeah. Obviously, in real cases, it's more complicated. Usually we have several red value or orange value. Yeah. But this is more easy. Yeah. So when we are working with dot balance, one of the first idea when we need to analyze this is to see the workload. Yeah? Is to see what is happening with my application, with the distribution of the work. And here, one of the first figure that we have is the useful duration. Then we need to see that what happened with the different duration in the computation for the different process. This is a histogram where remember that we have in the X, we have the time, and in the Y, we have the process. Yeah. So we observe here that in the case of the duration, we have a set of process. In some part of my histogram, we observe the zigzag behavior that I don't know if it's just yesterday what I commented. But the idea when we observe this kind, this means that we have some problem here. We have the process, some processes taken longer than the other. That this means could be we have some workload problem. Yeah. So to review this, we usually see the instruction part. Yeah. So here we relate this with the useful instruction. Yeah. So we can correlate this. And when we see the useful instruction, we see the similar behavior. So we can see that really the work is unbalanced. Yeah, it's related with the behavior of the application. It's not related with some relation with our system. Yeah, so this means that we have workload there. If you observe in that case, yeah, the workload is perfect in the instruction, but when we run, we have some perturbation there, but it's small really. So here we have different duration, but we will consider that it's not like this that is more, that have more impact in the load balance. Yeah, so there we have some, the source that that load balance is related with this. Really the application is doing in some part of the code unbalance. Yeah, so this is not the follow of the relation of my application and the system. It's of the behavior of the application. So the good of the Paraver, when we have this kind of histogram, we can obtain the timeline for that part. Yeah, we only need to zoom in that part and we obtain the timeline where the problem is. Yeah, so here we can see that one part of the 10 iteration that we have in this example, we can observe the different duration and we can set the load balance. So in that part, we have the load balance. Also in the hands-on, you can see that we can relate this with some part of the code, but also calling the caller view, where you can relate the part that is unbalanced with the source code and review what is happening there. Yeah, I think that if you see the hands-on, you can see that part with more detail. So this is with MPI. This is the idea when we use basic analysis. What happened? We are working with open MPI, but plus OpenMP. Okay, here I will try to don't focus a lot here because this is all a model that, remember that basic analysis implement model. Yeah. So in POP, we have the classical model that we apply in MPI, and we have different model for MPI plus OpenMP, and that's the pain of the different tool. But the idea that all of us have similar definition. How we implement the OpenMP, the MPI plus OpenMP model, we consider that we have an parallel efficiency that we can express less the multiplication of the basic metric that is load balance and communication, but also we can express this that the multiplication between the two paradigms that we are evaluating, that's MPI and OpenMP. Yeah, so this is our idea. We can prove on that way. But also, this means that my MPI part will have a load balance and communication, and similar to the case of only MPI, we have serialization and transfer. And for OpenMP, we have also the basic metric, load balance and communication efficiency. Yeah, so it seems a little complicated, but also we can express the hybrid load balance as the multiplication of the load balance of the two paradigms that we are analyzing. Yeah, and it's similar for the communication efficiency. This is the model that we implement in basic analysis to obtain the different metrics. But how we can work with this? Because we calculate this, we compute this as a percentage, but we have the efficiency metrics mixing, and so we need to separate what's the part that corresponds to MPI, what is the part that corresponds to OpenMP. So we need to decide where blame the inefficiency that we observe there. So one way we do this is to send the API plus OpenMP hybrid program in that way. Remember that I think that Marta displayed, and also Herman, that we have two states here, that MPI and used for computation. But when we are working with OpenMP, we have also the OpenMP runtime. Yeah. So what is our idea? We think, okay, usually we work with hierarchical code where the MPI is the upper level. This is our basis. Yeah. So if we don't have this kind of code, our model is not applied. Yeah. So we can apply our model in other case. We need this. So this is the computation, and we consider that the worker threads is not doing nothing when the master thread is doing MPI. This is our idea for our model. Yeah. So from the point of view of the MPI, all that is not MPI is computing. Yeah. So that part is computation for us. Even they're related with the OpenMP runtime. Yeah, this is the way that we compute our model. So here we have some uses that we need to take into account, that OpenMP metric with the byte metric as the residuals of the other part, that is the MPI component. This means we first compute MPI component, and after that we compute OpenMP. What means this also? So this means that any efficiency degradation that we don't blame to MPI is attributed to OpenMP. This means that the way that we take this. And also this means that all the inefficiency that we measure outside the MPI is also associated to OpenMP component. Yeah. This model has some discussion, yeah, but it's not displayed to discuss this, but this is working in that way. We remember that the different options that we have here, and remember how we plan this. And remember that you can apply this if you have a code that is this kind of hybrid hierarchy. Yeah. So we will apply the basic analysis for the Lulish also, but for the version, but MPI plus OpenMP. In the case when you run a basic analysis, you obtain several tables of metrics, and one of them is that the global efficiency, where you can see the parallel efficiency with the two basic metrics, that is load balance and communication. And you can see that here is the load balance, the parallel efficiency is very low, and it's related directly with the communication efficiency. Yeah. But also basic analysis provide us the hybrid parallel efficiency. Yeah. And we have the efficiency for MPI and the efficiency for OpenMP. Yeah. And you can see here that this communication, remember, we are working with a multiplicative model. Yeah. So this means this is consequence of the MPI communication and OpenMP communication. Yeah. So this low value is mainly related with OpenMP and not with MPI. If you observe, the MPI communication is really very good. Yeah. It's near that 100%. So, okay, our model say the problem is in the OpenMP communication, but usually we say, but what is communication in OpenMP? Because we have communication in MPI, but in OpenMP, it's stranger to speak about communication. In our case, in our model, the OpenMP communications represent the OpenMP runtime, the overhead what we introduced with OpenMP runtime. Yeah. So this is our focus. Remember, we don't have communication really, but when we are working about this, we are working about the OpenMP runtime. So how we try to explain this value? Remember that from the point of view of MPI, we are only focused in the threads, in the master threads. We have an outside MPI. Yeah. So this means that for MPI, this is like computation. But really, when we evaluate what represented outside MPI, we have several states associated with this. Yeah. If you observe here in the master thread, you'll see that, remember that usually when we see this kind of table in Paraver, the blue means that is taking more time. Yeah. If you observe here, the more significant is the scheduling and for join, and after that, the running. This means that the master thread, the different master thread is taking more time doing scheduling for join. And how much represent this? In that case, is near to the 80% of the time. This means this is the time where we are spending with the master thread, only in the master thread. Yeah, this is the reason that this is one of the part that is doing the low value in the communication. But what happened when we are analyzing this in more detail, but focus in one thread and the worker thread. Yeah, only in one iteration. What we see here, we have here two main parts that we select this. One that we see that, okay, some imbalance there, and also you can see that some thread is doing more work, and we can see here in the running, like, and in the average runtime that really there are some thread, the worker thread that is doing more work that the neither. But also we can see in that part, the other part of our application. But this is one iteration. This means we have 10 iterations with similar behavior. Yeah, we can see that really here in this small part, the bars is really very small compared to the either and some parts related with the synchronization that we have also in that part. Yeah, so here we can see that really this iteration have some problem there. When we evaluate all the iteration, only in focusing that iteration, seeing the different state and the percentage of the time, you can see that as we see what the master thread, we see here the master thread obviously is taking more time in the scheduling and for join, and the threads, the worker thread is spending more time in either, is doing nothing, yeah, in this part of the iteration. So this is also some problem that we observe in the part of the communication, yeah. So this is the reason that we see we see low value in that metric. But if you see, we need to research several issues to investigate, because here we have some behavior and here we have others, so we need to focus in each part. It's not easy usually, but here the idea of basic analysis is try to give you an initial idea, and after that you can focus only in one part and apply again the basic analysis to see the other metrics only for one part. Yeah, this is an iterative work really. Okay. This. So to take the metric for the MPI plus CUDA, before you need to obtain the trace, yeah, with MPI plus CUDA. So here, I suppose that all of you work with this. You obtain the traces with for MPI, for normal MPI, yeah. When we are working with MPI plus CUDA, you only need, in that case, you have the script to obtain, but that is very important that we need to use here. In that case, we are mapping 4 tasks, yeah, one for each CUDA devices. You observe here, we have 4 CUDA devices, and we are using 4 tasks, yeah. And here is the number of CPU per task. And remember that we enabled this to obtain the hardware counters. We need to load the OpenMPI, but also we need to load the CUDA. And here, this is normal. You need only to put here your binary that is using MPI plus CUDA. And the other important part we change here is the trace.ch script. Yeah. In that case, we need to select, in green here, you can see, we need to select the library that is for CUDA plus MPI. Yeah, this is a very important part because sometimes the people put here the wrong library and you can obtain the trace. So remember, select the right library. In that case, it's CUDA plus MPI. Yeah, and also here you need to add this to add multi-device support. Yeah, all this is really in the folder of VCC tools, so you can take it from there. And the other part that you need to change, yeah. Okay. Please, you need to copy again the VCC tools because we add there the current material, yeah, the material that we have today. And here, remember, the other thing that you need to enable the CUDA, to trace CUDA, yeah? Obviously, you need to enable also MPI. Yeah, remember that the XML is where you enable the different part that you want to trace, yeah. So by using this, you only need to send your script alarm to, remember, use your reservation and with the account, and you can, if all is run fine without problem, you will obtain the cover leaf traces, yeah? And we can apply in this basic analysis, yeah? And after I finish with basic analysis, Lau will show you more detail about the traces, yeah? Here, when we apply basic analysis, remember the basic analysis implement different models that we define in the POP project. Yeah. So in the case of MPI plus CUDA, we implement the type model. That's the model that Marta explained. Yeah, this is a model that we have the parallel efficiency for the host side and for the device side. If you observe here, we have the similar scheme. In the host side is multiplicative and in the device also, but it's not multiplicative between device and host. Yeah, it's different models. And you observe here is similar. We have computation scalability, we have MPI parallel efficiency with all the component and submetric. And here we add in the host side a new metric that is the offloading efficiency. Yeah, this is the only part that relates the running in the device with our application in the host. Yeah. After that, we have the device part. In the device part, if you observe, we have again the basic metric that is communication efficiency and load balance. And we add a new part, a new metric that is the orchestration efficiency. Yeah, that is the measure of the efficiency when we are doing useful work in our devices. We need to see the definition of all of this. Yeah. So here, this is the definition of the different metrics that you can read when we are analyzing. Yeah, I think that Marta also explained. I put here the new metric, really, that is more important for us, because the other is that the usual metric. Yeah. So when we apply this is a new case. It's not Lulesh. It's a clover leaf. Yeah. And here, when we run basic analysis, we need to say that we are using the type model. Yeah, I put this in the first slide that we ran in Mare Nostrum. You need to select the type model to obtain this table. If you observe here, we have two parts. One is the host, and the other is the device. Yeah, this is the device part, and this is the host part. If you observe here, we obtain a very low value here. Yeah, remember this is a percentage. This is a very low value for the offloading. Yeah, and the other part in the device, we move here. Sorry, I put there the definition so you can remember the definition of the metric. Yeah, the efficiency to the use of the accelerator. This part, some people don't like it, but I think that is very important to put how we compute the metric. Yeah, because we can understand how we obtain the value from the traces and obtain the metric. So we observe here the offloading is the ratio between the total useful of the process only. This means only the process that we run in the host part over the total of the offsite MPI. Yeah, this means that this metric is only focused in the process of our MPI part. Yeah, and this is a metric that we obtain in the side of the host. And the other that we can see that we have here also, it's not low value, but between the other is one of the most low value, yeah, that have impact in the parallel efficiency. Remember, these three metrics we multiply to obtain the parallel efficiency at the patch level. And the orchestration efficiency, yeah, is that measure the inefficiency or the lack of available work to do. Yeah, as you observe, this is the way that we compute this. This depends on the useful computation, but in the device. Yeah, this is focused in the device and the memory transfer in the device. Yeah, so this metric is only focused in the number of devices that we have, and over the total time. The total time is the time of all our running. Yeah, it's not only the time that we run in the GPU, it's all our running of our application. Yeah. So we will try to understand why the offload efficiency is very low here. If you observe here, we only focus, remember that that metric is only computed by using the MPI process that we run in the host. Yeah. When we are working with the useful, here we can see this is the useful time. Really small. Yeah. And the other side, we have the offsite MPI. Yeah, this means that if you observe, the offsite MPI is higher than the useful computation. This means that there are a lot of work doing outside the MPI. Remember that when we need to analyze this, we need to see what means this outside MPI. What is the different time that we have there? So when we analyze this, when we focus in the CUDA call, yeah, if you observe here, we have different time, and we have that the CUDA device synchronize is taking more time of the MPI call, yeah, and this is the time that is spent in the CUDA call. If you observe, this is for the MPI, this is outside MPI. If you observe here, yeah, this is near to the total outside MPI. This meaning all the time is more in the call of the CUDA. Yeah, so if we analyze this, we observe that in 90% of the outside MPI is really spending CUDA call. Yeah, in that case, this is the timeline of Cloverleaf. For some reason, this application is doing a lot of device synchronization, and this has impact in that we observe in the path of the device offloading. Yeah, so this is a reason that you can see this, or you can see more detail about this part when Lau present how you manipulate the trace. Yeah, but the idea of basic analysis is also to give you some idea where you can have some problem, and you can research there, and you can apply the different tools that we have to research more about this part. Yeah. And what happened with the device orchestration efficiency? Remember that in that case, we have an 80%, 88%. I think that is not very bad. But this is a metric that we measure in the device part. Yeah, we remember we use the useful and the memory transfer. That here only in the device. Here we have the 4 devices. And when we see the timing, we can see that the maximum is for this device, where we have this running and this memory transfer. Yeah, and the rest, the remaining execution time, where is the remaining execution time is in the either and the not created. The not created state is related with when we start to register the stream of the stream that is running in the GPU. Yeah. So when we analyze this, we can see that really the orchestration efficiency is mainly affected by the idle, that is represented at 10%. That is in no big value, but this is the reason that we obtain 80%, 18%, I think, in the device orchestration efficiency. Yeah, and only one in the not created. So that is the part that is measuring our efficiency that related with orchestration is not so bad. But we can understand what is doing the metric. Yeah, and when you have a low value here, you need to review where is happened with this path, possibly in an idle state is taking more. Yeah. So this is the different part that we have with basic analysis. If you can test in the Mare Nostrum. I think now Lau can explain more in deeper the MPI plus CUDA traces. And after that, I think that it will be a very good idea to apply basic analysis to your application. Yeah, because really the problem are very different. In this case, it's really easy to see the problem, but in real cases, it's more complicated. So I would like to, I suppose, after the lunch, we can apply in your cases. Yeah. So now I finished with my presentation. I finished.
Hands on how to look at a hybrid MPI plus CUDA trace. I don't know if you got the trace with, well, you did. Sandra showed this. I don't know if you got the trace. If not, please do, because we will use it. If you don't want to take the time to change everything and to run the scripts, the traces are already prepared under the traces folder in the BSC tools folder that yesterday you copied. I think the trace should be there. If not, just SCP again and grab the trace and to your laptops, and then we can start analyzing the trace. This is a new application. This is Cloverleaf. It's not Lulesh. Cloverleaf is parallelized with many paradigms, MPI, MPI plus CUDA, heap, OpenMP, a lot of them. For this case, we will use MPI and CUDA, pure MPI and MPI plus CUDA, and a small input that it's shared with you in the folder. The first thing we will do is to compare the two runs, the MPI and the MPI plus CUDA runs. The MPI run takes around 90 seconds, whereas the MPI plus CUDA takes only 5 seconds and a half. So it's a 16x speed up. So a lot of speed up. So the CUDA parallelization seems good enough, right? We'll not look at the MPI trace. We'll look only at the MPI plus CUDA trace, which is the one, the MPI case. We already did it yesterday. So today we will focus on the MPI plus CUDA. We grab the trace and to our computer, open Paraver, and as always, file load, and I have the trace somewhere. Cloverleaf, this. So as always, by default, Paraver shows you nothing. The first thing we will do is to take a look at the efficiency model, the efficiencies of this trace. We will take a look at all of them and to see what the hosts and what the devices are doing. So we will unmark this show totals only, and we will open the control window to focus on the iterative part, which is this. The first part is not parallelized, it's just initializations. So we focus on this part, and as yesterday, we will copy. It's slow, the sharing. Copy and paste the time here. So we can close this. What do we see here? That the hosts are mostly doing nothing, no useful computations, and that all the work is done by the GPU. So almost 90% of the work is done by the GPUs, 0.5% is done by the host. So it's a usual way to parallelize things with CUDA, where the host just is the orchestrator and the devices do everything. So let's take a look at what the host is doing, right? By do so, we will start by taking a look at the CUDA views. So the first thing will be to open hints CUDA calls, which open a timeline. You can do right-click copy and paste time to focus, to select our focus, our region of interest. We can select object. We can generate a profile with here. Can't we open a profile with this? Yeah, CUDA profile. Sorry. Instead of CUDA calls, open CUDA profile, which will open this. As before, we will show everything. So click on this sigma and copy and paste the time again. Paste time, so focus on our region of interest. And what do we see here? That 80% of the time, the host is doing CUDA device synchronize. So it's waiting for the devices to communicate with them. 7% of the time is doing mem copies, and 6% of the time is doing CUDA launches. So that's what the device is doing. Okay, we can take a look at what the device is doing in the part of MPI. So what's the overhead of MPI? Because we're looking at a hybrid MPI plus CUDA trace. So let's take a look at the MPI profile. In this case, we can select only the objects. In Paraver, we can select a few objects. So in this case, we're a little not interested in the devices. So we can look only at the host objects by right-clicking, select objects, and remove the CUDA devices. We'll click on the zoom. So, and this is what the overhead of it. Sorry, I didn't copy the time. So just right-click, copy, and paste the time. Or I did, I don't know. So this is what the host is doing in respect with MPI. So, 3% of the time in MPI. So it's around 96% of the host time is waiting for the device, and just 3% is MPI overhead. Now we can look at the CUDA kernels. So right-click hints CUDA kernels. We have a timeline. We can select the objects. In this case, we will just select the CUDA devices. Okay. Right-click, copy, and paste the time. Seems like there is some interactive. So the color repetitive. We can generate a profile of this with this button, new histogram. We select the current timeline and click on OK. And hide the empty columns. We'll put some colors here. So, and we have all the kernels here that are launched by what device. We can reorder these, so we have the kernels on the y-axis, and it's easier to see their durations. So for this, we'll this H here changes, and we can sort by total. So at the top, we have the one that is taking the more time, and at the bottom, the one that is taking the less time. So the per range to the kernel is the one that takes the most. And we can change the statistic to see the percentage of time we are in this kernel in each device. Okay. And at the bottom, of course, we have the total. So we are 90% of the time computing kernels, which we saw before, right? We can also look at how well the parallelization of these kernels is. So, I mean, if every kernel or every instance of the kernel does the same amount of work. To do this, we will look at the take the same. So at the histogram of computing time, and copy and paste the time as always. Zoom on this region. We will select the objects to only focus on the accelerators. So, and it seems that all the devices take the same amount of time doing their work, right? We see straight lines, which is what we expect to see in this kind of histogram, histogram of duration. But we can focus only on one of the kernels, for example, because we have a lot of kernels. So maybe the straight lines are mixing kernels, right? So maybe these and these are the same kernel, but the histogram shows them in the same straight line. We can do this by adding a dimension to the histogram. This is a new this is a feature that you didn't see yesterday. So the same kernel names with the same colors. Cannot open this. I don't know how to open this. Maybe here. Okay. So we have a question here. Why are the same kernel names? Oh, okay. This is because of so every kernel name is a CUDA launch. So depending on the parameters of the CUDA launch, Paraver gives Paraver extra gives a different kernel because the address is different and things like that. So we are thinking on what to do in these cases. If maintain this, because each kernel name, we can take a look at each kernel name and you will see that
templated kernel.
That these are parameterized differently.
It's the same, but the arguments of
the arguments are different, right? So
these are different kernels,
right,
but it's the same template.
it's the same thing. And we have to decide whether to keep it like this or we have to decide. I mean, it's a discussion we had.
Or to have a layer of collapsing.
That's it. Or maybe give you the option of collapsing or seeing it collapsed or without. So that's the reason, because this is the same kernel.
Maybe you can show where you can see the arguments of the.
Yeah.
Well, yeah.
So yeah, the new dimension in the histogram. Okay, Paraver is very flexible, as Herman said yesterday. So it's almost a computer inside a computer. You can do anything with the data almost. So as I was saying, maybe these straight lines are mixing kernels, right? So we can focus on just one by adding a dimension to this histogram. To do this, we'll have to go to the main Paraver window. Sorry. And this properties mode, we have to change it from basic to full. And in the data window here, select on the data window here, select the CUDA kernel option. Sorry, no, not like this. Sorry. In the 3D here, was it useful or was it another thing? So not the data in the 3D window, we have to select the CUDA kernel. No. And Paraver crash.
It's like demo effects.
Yeah, but why always me? Come on. Okay. I will open the CUDA kernels. The Instagram computing time over here. I will zoom here. Copy and paste the time. No, no. Zoom in this part. I can select the objects again. In here, change from basic to full. 3D, please don't crash. CUDA kernel. Okay. And here now we can select any of the kernels that the application is launching. Okay, we select the first one. The first one is a straight line. So every device has the same amount of work in this kernel. The second one only runs on 2 devices, but maybe, as we said, is a different instance of the same kernel. So it's the discussion we had. So maybe we'll have to join them. But you can select any of the kernels and see if they are really taking. This one is not. So you see, you can focus on any of the kernels and see if there are some of the kernels that is not straight line. So not all the devices are doing the same work. And what else can I show? The transfers, I think, something like that, maybe. I don't know. So yeah, let me focus in one of the iterations here. Maybe select this. What? Come on. I opened CUDA also. Look at the mem copy, select it seems to be an iterative region. We can compare with MPI. So you can see if this is iterative. In here we copy and paste. You can also copy and paste the objects. So it seems that is iterative. I don't know if you see it well, but in here you have pink colors, which in MPI it's the MPI already used. So this is a small zoom of the parallelized region. So it seems that is limited, that every iteration of the parallelization is limited by the MPI already used. We can focus on one of these. And copy and paste the time. We can open the CUDA device synchronize, CUDA mem copies, and we can see what everything that it is doing. So we are interested, I don't know, in the mem copies. With this, we can select this color magnifying glass, select the mem copy, and we know where the mem copies in each iteration are happening. So at the beginning and at the end, which is not strange. We start by copying the data we want to compute, and then we graph the data. I don't know what else. I have 10 minutes, I think. We can take a look at the size of the mem copies, maybe. Just to, so I don't know. So, but for this, I have to do. Or open the CFGs that we have prepared, maybe, and see how the kernels are executed on the device. So for this hands-on, we prepared a couple of configuration files in Paraver that are not distributed with the Paraver installation. You should have them in the BSC tools folder inside the CFGs folder I created this morning, I think. So you will need to recopy them. I have them here. They are named low configuration. Let me go to here, BSC tools, CFGs. You should have this. So these are already shown. Well, this is the main copy size to copy paste, the time, and it shows the size of the main copy, which is 2Ks. Okay, so you can also know the size of the main copies. But I wanted to show this kernel block thread CFG, which I think it opens just okay. This shows the size of the block, okay, the number of threads per block that the kernels are using. In here we see the size, 256 threads per block, and this is the number of what is this? The number of kernels per block.
That's
the number of kernels in
launcher. That's how
total.
this configuration of
Okay, yeah,
thread
right.
size.
That's it. And what else? I don't know.
Below you have the grid size also.
Yeah, it opens more than. And this is the grid size, which is we have some kernels of a small grid. The grids are the blocks are organized in grids. So we have grids of 16, 31, and 256 blocks, so a small grids, and then we have very big grids of 115,000 blocks per grid. So we have around 15,000 grids of using small blocks, and the rest, it sums up to 3,000, I think, or something like that. They're using a lot of blocks, so big grids. What we can change these statistics, I think. So instead of well, yeah, that's it. So I don't know. So you can look a lot of things, different things, and you have these CFGs prepared for you. So maybe I don't know, in the afternoon we can help you to see these things if you have a CUDA trace. That's it. You know, we have 5 minutes, I think, but maybe less.
5 minutes, the clustering part.
No.
With it. As I mentioned before, you have it in the slides, there is a full hands-on how to use the clustering. It's super straightforward. And then in the afternoon, if you want to try it, we can help you follow this.
You also have an OpenMP example if you want to take a the OpenMP example.
But I'm not sure if I could find the traces for this CUDA example.
It's in the BSC tools folder that you copied yesterday, but maybe you need to recopy it today. But the traces should be there.
only half an hour. The idea of this presentation is that we'll move a little bit to what do we do when so this started all with some use cases that we found. What do we do when we need some tracing capabilities that we cannot find on our current tools? Maybe because they're under development, which is the case of Extrae, or maybe because there will always be this advantage from the from the people who do the hardware. The disadvantage that we'll have to collect some data or to collect some complex behaviors that will take more time and more engineering effort for us to integrate it to our tools. So we found some specific cases where it was useful for us to get traces with Nsight Systems, which is the NVIDIA's proprietary tool for tracing applications in general, but specifically, of course, when they use GPUs. But it traces everything that happens in the system, so mostly every programming model and almost all the behaviors that you can find in the CPU and in the GPU. And we found useful to get traces with Nsight Systems at some point, but then we saw that we wanted to leverage the capabilities that we have in our analysis tools, in the analysis tools that we have at POP and here at BSc specifically. So that's where the title from this presentation comes from. That's getting Nsight Systems traces and translating them to Paraver. Uy, ¿qué está pasando? Ahora. So the thing is, I will talk a little bit about how do we need to jump, when do we need to jump to Nsight Systems? So in which specific cases, which kind of applications, or when you will detect that maybe a trace from Nsight Systems will give you more information more information regarding the performance that you cannot get right now. What can we see with these translated traces that we cannot see either from a regular extract trace or directly looking at Nsight Systems? And finally, I'll show you how to do it. So mainly what I want is that you to have a brief idea of when this is useful and what can you do with it. And if this afternoon you have an application or a use case that you think that this can fit, I'll be around and I'll get more into the hands-on part with you and show you how you can benefit from it. As an overview, we have Extra and Paraver, which you know already. You had sessions for it, and then we have NVIDIA tools for NVIDIA GPUs. This is focused on NVIDIA basically because we have H100 GPUs here at BSc, but you can, I mean, the ROCm sys profiler for the AMD GPUs is more or less inspired by the same idea. They have the same hierarchy of tools also on AMD. So more or less you can extrapolate one thing to the other. But here the thing is that this is focused on NVIDIA. We have Nsight Systems on one hand, which is, as I said, this overall system level overview of what's going on, with system level information, the behaviors to study, so how different resources synchronize between them, how parallelization works, data movements around. And we can more or less we can visualize the traces with the same tracer, and I found it to be usable up to 8-10 different processes or resources. But the good thing is that they have all the information and on the programming, on different programming models, specifically in CUDA, and on what's going on inside the GPUs. Then if you want to go even deeper to the kernel, so if you want to understand the behavior of a specific kernel in terms of architectural performance, then you have Nsight Compute, which basically analyzes a kernel isolated from the other. So this can be useful when you are really sure that you have a performance issue, or when you are focused on optimizing a very specific kernel for better using the massive parallelism architecture that you have inside the GPU, but this is run isolated. And this is important because usually when we run kernels on the GPU, they are not run isolated. They run with other kernels. We sometimes want to overlap them with other kernels or communication. So studying the behavior in the Nsight compute can be useful for some things, but can hide some realities on the other hand. So that's why we focused on Nsight systems, and what we try to push is that mainly with Nsight systems, you can see most of the things that you need to know about your application. This is summary. System level overview and individual kernel, and then we have the VS-Extra and Paraver, and the proprietary tools. So when we should use Nsight systems, these are some of the use cases that we found. Basically, the main limitation for us was where we found the new distributed parallel runtimes that were not the classical HPC distributed runtimes like OpenMP, OpenMPI. Sorry. The most applications used, the primary use case for that, or the primary application was when trying to analyze training or inference of LLMs, that they use the PyTorch communication backend for acknowledging the processes and starting the communication, and then for the data plane they use Nickel in this case for NVIDIA. This was a limitation to get traces with Extrai because, of course, so this was not supported at that point. So we could not get this distributed large-scale traces. This was one of the limitations. Then there's when you want to have an overview of GPU metrics. This is something working, trying to support on Extrai, but it's difficult. It's something that we already see it's difficult. But instead for Nsight systems, this is something that they just do because it's their software, it's their hardware, and they know how to do it. And we can already get a set of GPU metrics that, although they are not very as detailed as the ones that you can see with Nsight Compute, we found that they are they provide enough information for most of the things you need to do. If you have instrumentation within VTX, which is the instrumentation library from NVIDIA, you can instrument your code with lots of things, but sometimes what we found also is that some applications or some frameworks already have instrumentation in NVTX. So if you want to see that, you either capture this instrumentation, this region with your tools, or go to Nsight systems. If you have mix of multiple programming models, or we also found it as a way to get all the information that we can, and then try to see what we can get in our own tools, or if something was wrong with our tools or that we needed to validate. This was also, we consider it a source of truth, although sometimes it is not, because they also make mistakes. and the message here is that we do this to get more information, not because that we think that their tools, the proprietary vendor tools, are always correct and they always give us the correct solution or all the information, because what we see in this specific case is that we don't like their visualization, for example, and we try to jump to Paraver. So it's not, the message is not they are always correct, but they are sometimes, it's sometimes useful to consider that as this source of truth for tracing. If you want to do profile with Nsight systems, you just need the binary for it. It's not something you need to install system-wide, so it's handy. It's very handy, and I have to say, you just download the package on your home and you just leave it there and call it like this, and you're good to go. It doesn't need to match any CUDA version that you have. Just keep the most recent version of Nsight systems, and you're good. We can also, as with a lot of other tools, we can also we can annotate with NVTX. I already said that, but then we can activate or deactivate the tracing with by calling the API of the tool or by NVTX ranges. This line up here shows us that we can just signal Nsight systems to capture during the range that we say here, in this case, range name. If we put a range name there, it will only capture during that NVTX range. This is very useful when applied to the POP methodology that I think there was a session the first day. So if we know that our application is iterative, we don't want to trace the whole application, and we already know that maybe we want to discard what's happening in the beginning, so we can already, like, this is pseudocode, so you can, in the case of a LLM training, you can imagine how this goes. You just train for a few epochs, you discard the first one and the second one, and on the third one you start the profiler, and in the following one you stop it, and you get a whole epoch, a trace of a whole epoch, but only you know, this one iteration. About the GPU metrics, this is the things that you get more things, but these are the the ones that I find more interesting. These you get for free. Let's say you only need to put this flag, GPU metrics devices, and you get this for free. You can get them to a actually pretty fine granularity, so sampling rates up to 100 kilohertz. This is useful, and it really allows you to see to have many different samples inside a single kernel. So you are even able to see behavior inside kernels, and we can have things like the issue rate of the string multiprocessors, the activity on our tensor cores. So it's a way to see if our, in theory, specialized matrix multiplication kernels are actually using the tensor core of our GPUs, that we've paid a lot for them or not. And some network things like the bandwidth on NVLink or the bandwidth on PCIe, which helps us to validate, for example, when we have communication issues, when we have long communication calls, we can maybe with these metrics we can validate if we're actually sending data, or if we are always hitting the bandwidth limit, so meaning that we're actually moving data around and this is the limit, or that if it's something else that's blocking us. And the last one helps us to see if we're giving enough work to the GPU, or if this work is able to the threads are able to hide the latencies of the others. So it's a pretty complete set of metrics, actually, and with all of this, you can already get a rough idea of how your kernels are performing at the very low level without the need to go into compute. So now we have an Nsight system traces. What can we see or do when we translate it to Paraver? Basically, with Nsight systems, you get a different report for a different node or process, depending on how you launch, how you use your launcher, SRun or whatever. But the overall thing is that while in Extrae we already have its own merger, which acknowledges each process and knows that this is a distributed run, and they just merge and align everything together at the end of the tracing session. This doesn't happen with Nsight systems. Each instance of Nsight systems, it's going on standalone, and they don't know anything about each other, and they give you a different report at the end. You can still load all of those into Nsight systems viewer, and they will and it will stack them up all together. but again, you will have to do this, and the visualization when you go for higher than 10 processes, maybe 10 resources, it's not really feasible to analyze something. So what we can do is just get these different metrics, different reports for each rank or each node, and then we can merge all of them together with the translator. The other thing that we can do is that we can compute efficiency metrics. So we have the POP efficiency model that they already showed you also. But if we can get traces, if we can translate these traces to Paraver, we can also compute this efficiency model, which is very useful for the analysis. We've been working in an extension to this model to include the behavior on devices also, and this is more or less how it ends. We have load balance between the GPUs, communication efficiency, which more or less tells you the time that you're losing because GPUs are moving data and only moving data around, and this includes memory copies, but also nickel communication. So communication on the NVIDIA communication library, and then orchestration efficiency, which is basically the rest of the time, the rest of the inefficiency, which we give to the fact that the CPU is not giving enough work to the GPU. Then we have the set of device computational scalability metrics that these are to be defined yet, but this box here, it's a lot of things that we found that are like alternative metrics. So this is all things that you can compute now with Paraver, with a single trace of Paraver, that we have found that they can be useful to see depending on what is your case. You see that, for example, MVU is very specific to language models, but communication and compute overlap. This is something that applies to more or less any kind of AI or classical HPC application, and those are very other typical, like the raw metrics. So now jumping to the translator, finally. The summary is that we can get to translate all these Nsight systems reports into Paraver format, which are these timestamped events. So we get all the information from Nsight systems that is sometimes hidden or just displayed there, but not actionable. We get it to timestamped records in Paraver, and in Paraver everything can be plotted as a function of time or resource. So we can compute anything that we want with our data. We can merge these multiple execution reports into a single trace, and we also provide a full set of CFG files, configuration files for Paraver, to compute all of these metrics that I've been talking about, including the efficiency metrics. You have it installed in the shared folder of Mare Nostrum 5. So if you, I'll put the path now. So if you want to use it later this afternoon, you can get it just a Python package. So you need to source the environment that I created for you, and then you can run the tool directly. And you should run it like this. You have this flag, you tell the things that you want to translate. Right now, this is, although it's been some months already working on this, it's still under development. So it has not a stable, like, finished API. And for example, something that we want to support is being able to automatically detect what's the information available to translate it. But right now you have to tell it specifically the things that you want to translate. So good API calls, GPU metrics, and NVTX in this case. You put the list of reports that you have, and you end up with a trace. And the workflow that we end up with is this one. We can add a CUDA application and translate it with the translator, and we get a trace that we can do trace analysis with Paraver. You have all the CFGs that I told you also in the shared folder, and then we have the performance metrics and other tools that right now we're working on extending the model factors, the basic analysis toolset so it can like be general and support all these translated traces also. And these efficiency metrics, this is under development right now, but we have a much simpler script that does this, that computes these metrics. It's very, very much simpler than basic analysis, but it gets the numbers and can tell you the model that I showed you earlier for a translated trace. And this script is also in the shared folder. And finally, so if you want to translate a trace, you just have this. You have to load some modules. That these are the list. I can paste it somewhere, maybe in the Zoom or. You activate the environment, and then, as I told you, you just put the different reports and you translate it. And that's the end. So the thing is that if this afternoon you have some traces or some use case that you find maybe that with Nsight systems you can get more information, we can translate those traces and see if the CFGs that we have, we can see more, we can get more insight on performance. And that's all, I think. Okay, 5 minutes left. So if you have questions or.
As you found the tool. So if everyone can hear me, let's work, I hope.
Yeah, perfectly. All good.
So now we want to continue our work with the Scalasca ecosystem. And in this session, we were looking first at Scalasca, going basically, if you remember from yesterday, we were looking directly with Scorpy and going just up towards profiling. And now we go the step further and do the tracing and do the automatic trace analysis with Scalasca. Afterwards, we are also looking into what's different with measurements if you are adding GPUs to the mix, and seeing hands-on part with and the second test code we have in the system. And afterwards, a few bit of additional information. But first, we want to start with this session with the introduction to Scalasca. Scalasca is designed as an automatic trace analysis tool, which provides you with automatic analysis of the information and presents this afterwards in a concise format using the cube data format. It supports the most popular parallel program paradigms, like where the current focus is on MPI, OpenMP, and to a degree everything which is pthread based. If you are just looking at the host side events, you also can use this for applications that mix MPI, for example, with CUDA, OpenCL, or OpenACC, in a combination where you want to look at the application as a whole, but with limited information from the GPU side. It's specifically targeting large-scale applications with a high scalability. And the current latest version is 2.6.2 from last April. The basic ideas we are looking for is the automatic search for patterns of inefficient behavior, to classify that behavior and quantify its significance. it should also not just show the problems itself, but also identify the root causes and the delays introduced through waiting times. The basic concept works on looking at the whole trace, the big data, and reduce it to a high-level result that you can analyze in timely fashion in this case in Cube itself. It's guaranteed to cover the entire trace. You don't have to look over every part manually, and the parallel replay analysis exploits the available memory and processors that the application itself uses. So tendency, if you're having application that scales to a certain degree, Scalasca can run on the same number of processes and threads and generate performance that's still in a range that it's usable for this application. It supports all major platforms. It uses the SCORP instrumenter as a basis for the creation of the traces, and it provides additional convenience commands for measurement analysis and post-processing. Like we will see for the Scalasca workflow, it combines and automates some of the elements we saw as manual steps in the SCORP measurement steps yesterday. We currently have some limitations. You cannot go beyond MPI's level thread funneled. And that is because we are matching communications one-to-one, and we have to, if multiple threads are communicating at the same time, that's not always guaranteed to mesh up and be able to replay in a reverse order. And as mentioned, that traces, in particular the events on the locations that are not the host site are problematic for Scalasca and cannot be used. While PABI metrics that are recorded are used but are ignored for the analysis and can later be joined again from the profiling information basically. To see the whole workflow as a whole, we start basically the Scalasca workflow with the instrumentation side of SCORP. This is the block on the left side here. And you have what I showed yesterday. Depending on what you are measuring, you have an instrumented executable, you set some hardware counters, and going from there, the first step is to create a profiling, what we did yesterday. And with the therefore get into the analysis with Cube, and you can get to the basic analysis. And this is the starting point to optimize your measurement configuration to a degree that you want to get before starting an actual trace measurement. And once we have that, we can generate from the SCORP measurement Scalasca a trace measurement which has multiple local event traces per process and location, and then run the parallel trace analysis afterwards and generate again a trace analysis report, which is also a QX file, which can then be viewed in Cube again. And the whole workflow, this block is technically what the Scalasca trace tools do. They work with the input traces, do the parallel analysis, and produce an output report. So now a bit on the topic of what we actually measuring and what the automatic analysis covers. And we define a few sets of patterns that we are looking for in the analysis. For example, the late sender, and this is a waiting time that is caused by a blocking receive operation that is posted earlier than a corresponding send. In this case, it's a simple case. We show here the timeline in an abstracted way, where if you start your MPI send later than the actual start of the MPI receive, you definitely can say this time span is a waiting time that's unnecessary and could be spent with more useful things by rearranging your computation. This also works with the variations that you have in point-to-point communications with I-receives and I-sends. The waiting time is then just generated in a different portions and usually in the MPI wait here, or if you're working with a MPI I-send and a blocking receive, you can see the waiting time still in the MPI receive. So the usually the starting points are the relevant point that have to overlap, and that's also what's done in the automatic analysis. We are sending around the pattern and the starting points and calculate the differences between the starting points and create the wait states based from that. This is just an example for the wait state. We have a numerous patterns that also cover collectives where you have waiting times at barriers, etc., and where the incoming times into the barrier are counted and generating how much waiting time you're seeing. And this is then reported as a metric in the cube viewer, how much waiting time you can have in the different MPI calls in this case, and which should be depending on their severity, be looked at. Further part is the example of the critical path analysis, where we looking at the trace and see where do we have wait states and which are the critical execution elements which are determining how long your actual wall clock of your program are. So these highlight basically the best candidates for optimization. In principle, you can optimize everything, but you usually are time bound with your working load. And so you want to look at the stuff that's really influencing your basic wall clock, and anything that's on the critical path is a good target for optimization, as it will likely reduce your overall time. Although, as I mentioned yesterday in the SCORP presentation, that once you optimize an event, like for example the first block of the critical path chain, things might behave differently, and you might have new things. You find new things to optimize until you are satisfied with your overall performance. So the third part is the root cause analysis, where up to now we basically spoken of the direct wait states that are caused by one specific communication element where one part has to wait on the other. Then we have basically the first part is the direct wait state that's directly caused by this send to this receive. But if you have a chain of send and receives, like in this case, the second receive is actually has a block of indirect wait time, because it's waiting of the waiting time prior chain in this communication pattern is causing indirectly. And the remaining blocks are then considered delays, because they are just happening because other processes are causing problem. So finding the root of your problem is helpful, because just fixing on a lower level in this chain has not only an immediate effect on this block, but if you want to remove a lot of the whole overhead, then you want to remove it, grab the issue at its root and remove the initial delay. These were basically the three main topics I wanted to present before going into hands-on with Scalasca. And that I'm switching out of this and going back to our basic setup for the hands-on. So we want to do continue the example basically we had yesterday with the BTMZ. And I go back. So you basically should have still the example folder from yesterday. In this case, I go to my user folder, the hands-on, the BTMZ. This is copy. bin.copy, the call path. So that was basically the status we left yesterday. And we are using the same toolchain, the GCC OpenMPI, and then with the respective SCORP and PAPI. And now we really need the QPlip and the Scalasca modules. Since Scalasca doesn't instrument itself anymore, in this sense, we still need the SCORP for doing measurements itself. So this is required as a part of the environment. And now we are here. We want to look at the prepared job script we have for the Scalasca run. I copy it first over and have a look at it. So the basics didn't change. We have the same setup on the SBatch side. We're still on the GPP partition. The use case is the same. Now we want to look at how to use Scalasca in the whole concept of the workflow. Scalasca can do also the control the run with the instrumented executable. By this I'm ending here. By prefixing the srun with Scalasca analyze or alternatively you can alternative you can call it scan as a convenience command and do a srun on these on the executable. The only additional setting for total memory is the 250 megabytes we calculated yesterday. Since we are not for the Scalasca one don't include the PAPI counters, that should be enough. And we're using the filter file that we also built yesterday. Or if you don't have it at hand, there's also a line for the prepared filter file in one below config SCORP filter file. So this is the only variables we're currently setting. And by default, if you don't send any other parameters on the command line, the Scalasca will do a profiling run, and we can show how this looks like. Let's see how fast this system schedules me out today. While doing this, maybe a few points. This is the scan command that can be used alternatively to the Scalasca-analyze. Basically, the Scalasca command covers multiple elements that can be called directly, and in this case, measurement run can be started by scan. You can set most of the configuration parameters by parameters to scan, but you also can use the configure options set by COSCOP. The precedence order is that you first take the command line arguments, then you use anything set in the environment from the SCOP variables, and if nothing else is set, you're using the defaults basically. Something went wrong. I probably should do what I tell people to do. So I should actually load my modules. In this case, I have demonstrated successfully what happens if you don't load your modules. So it just doesn't find the Scalasca command, which is helpful, is at least ends early. So now I'm having the setup for our toolchain, and I can rerun the something Scalasca is doing, and something you might run into it. If you don't set an environment variable for path, it chooses one itself. Something like BTMZ, which is the executable name, then the 32 times 7 from the process and threads it's running with. And also compared to SCORP, if there is already a folder like this, then Scalasca will abort. That's its default behavior, so it won't override it. It's slightly different to what SCORP does by default. If you have the same name, it renames the old one and hangs timestamp at this end. But that should be aware. Sometimes if you have a failed job, it's usually because you already had a similar name of an experiment directory in your current path, and then you should have just have to move it or delete the old one before, depending what you're looking at. So, let's see how fast. It's basically finishing, and it's done. So we see, oops, sorry, the same output of the BTMZ, but you get some information of output from Scalasca itself, usually prefixed by cscan, basically what it's running. And since we're in this case, as a default one, did just a profile, it basically ends after the profiling with just a summary measurement how much the collect time was after everything was done. The difference in time happens just because this is the application runtime, while this is the time collect after every overhead is every post-processing step is done. So the next step, of course, is you can now use something we did yesterday manually, and this is using square, a convenience command provided by Scalasca, and we can use the option --s on the SCORP BTMZ sum, and it will produce a scoring report and try to it does also the and also does automatically the remapping we did yesterday with the cube remap 2 and some longer options. It does it automatically. And if you're running it without any commands, it will do the remapping, and then it will start the GUI if you're running on the system where the GUI is locally installed. But in this case, we don't have the GUI we're not using the GUI on the system, so you want to copy the files over when you want to look at them, or using the SSR FS option we used yesterday. and we will go there in the next step. But this was basically just a fast rehash of the profiling step we did yesterday, just through the commands of Scalasca. And now we want to go in actually the tracing area, and we open up our Slurm file and do only slight modifications, and by adding essentially just a -t for tracing for the command, and it will trace. Now it's important that we have actually the memory requirements set. For the profiling itself, you could have run it with the default 16 megabyte, would have worked as well. But otherwise, this is not relevant. And we still keep the filter file. And now when we're running this, it will measure the run, do the tracing, and afterwards automatically start the analyzer in the same job. So let's see. It started already. Just while we're waiting, we can see a bit of the this Scalasca command itself is basically the high-level command that you can use to instrument, but you nowadays use usually directly scopy. The second one is that we can use the Scalasca analyze for the measurement run, but there you can alternatively go to scan, and for the what I showed you with square, you can also use the Scalasca-examine, and but the square is the the shortcut command basically. And if you have a case we won't be looking at directly today, but just for completeness, we have also additional where we can binaries where we can run the trace analyzer without doing a measurement first, using it on an existing trace. So we have a MPI one, an OpenMP one, and a hybrid one, and you can then do a srun scout MPI, and then on with the target of the trace folder where you have a prior trace measurement, and it would only run the trace analysis after on the existing trace. Right now, what we are doing, and the reason why we are showed this before, if we had finished with the current one does both in one step. First, we have the measurement run with the output of the BTMZ, ending in normal state. Then afterwards, we are getting into the analysis part where we start the analysis. Here's basically the srun of the Scout hybrid I mentioned before, and in this case it started automatically, and it goes through the different steps of the analysis and produces an output after a few seconds, in just 24 seconds in this case. Just as a comment, we have currently an error here, which is erroneous in itself. This has no direct impact currently. It's a combination of some issue in this copy end, but everything is written correctly at the end. So just feel free to ignore it. So now, if we have measurement with tracing and the analysis together, we can look at the output. So it produced a trace folder And now we see a few more items compared to the profile measurement. Since we didn't deactivate profiling, we still get a profile. If you're doing larger runs, you might want to deactivate profiling after you have set everything up and just doing this the tracing. Otherwise, we are still getting the Scopy config file. We are also getting the filter file, which is copied in after it's used. Or technically, the interpreted file is written out to the Scopy filter file. It's skipped a log file, which basically is the output of the run. And the scout.cubex is the result of the trace analyzer. It's also in cubex file. And then there are the traces folder, which is the OTF part, belongs an anchor file, which is the .otf2 file with some definitions file, and then the traces folder, which contains, if you have a look at it, the binary event traces, which contain files, 2 per location you're running, a definition on an event file. So the next step is again running Square, because we want the remapping of these files. And we're running the Square.-s on this copy. You can also run the Square, but it will then just complain that you don't have a GUI online. So, but right now we are just interested in the post-processing step. It might take a second. First, it takes in this case the profile and then the scout file. And the result with our default names for these are the summary is the remapped profile, and the trace cubex is the remapped scout file. And like I showed yesterday for the profile alone, it increases a bit the data, but at the moment we still can live with it. So the next step is we want to look at it. So now, if you remember, we used the remote use of cube, and in this case, I'm using the app image, and I have to. So I'm still in the folder of the last one. Now we are going on up, and here's my trace folder. No, sorry. I'm not try. No, I opened the wrong file. Sorry. I want the trace cubex. Depending how fast the file system and the SHFS connection is, it takes a bit, but for these comparatively small files, it shouldn't be an issue. If you remember our show yesterday, we are looking at first a relatively similar state. We have our 3 columns, the metric tree, call tree, and the system tree. The main changes we have on the left side in the metric tree, because what the Scout analyzer does is adding additional metrics to the metric tree. And we, for example, have the mentioned delay costs, which are, if you're looking a bit into the call tree, you're getting delay costs in MPI, OpenMP, and where there are contributions from these delays in the different call paths, and they are attributed the same as we had before over our call tree and system tree spread. The second one we looked at was the critical path. where you get basically critical path information for your call tree, which of the call paths have a huge contribution to the, or relatively a large contribution to the critical path, and make therefore good targets for analysis. I'm not sure why we have a negative value here. That shouldn't be. Also, if you ever see a negative value in cube, that's an error, because we shouldn't have negative values. But I'm not sure why this happened here at the moment. That's something I have to check later. And the third elements, which is basically the basis on which the whole also the delay and the critical path elements are built upon, are the weight states that happen for the various paradigms, and they are sorted in at the time tree for the different levels of the, depending on paradigm. In this case, I'm looking here into the MPI tree, where the are in the collectives, and we have, for example, weight at a barrier. In this case, not the largest case. We color that's on. And we, for example, we have also in the expand options that where we can expand the marked. So we have a weighted barrier, and it will expand to the ones that are marked. If you are looking at something which is a bit more interesting, you're probably looking at point-to-point. Our classical example of the late sender and late receiver for the one-to-one communication is, for example, here. And when we go there and expand the marked, we are getting the times where this happens the most. In this case, the larger contributions we already see are, for example, in the OpenMP and the synchronization part. Something we saw yesterday, if you looked at the topology elements, a lot in the happenings in barriers, and in this case, weight at barrier. And if we are here, have a look at the marked elements. And then we see that these are essentially the biggest contributors are the implicit barriers in the solver regions Xsolve, YSolve, and ZSolve. And if you're looking at these, that are these where we basically saw the split that the BTMZ doesn't really work with the 7 threads and just uses basically the first four effectively, and afterwards it's not really using them as much. And this is in this case attributed in the weighted barrier. Since we have quite a number of different patterns, it's also nice to see documentation that hopefully works. I'm not sure it didn't. Okay. Normally, there is, if you installed it yourself, the Cube client, you usually have it installed with access to a HTML documentation where basically every pattern is explained. And but thankfully, for the most part, weighted barrier or late receiver are quite self-explanatory. So we can, for now, work with that. And so the advantage of Scalasca in this sense is that we are getting the information about these weight states automatically in a concise form, and we can dive deeper into these if we have a specific highlight for these. And yeah. Looking at these. For now, I want to switch depending on the time. Yeah, I now want to see what happens to our measurements and analysis when we are adding GPUs to the mix. So for now, we can close this measurement. And now we want to switch to the GPU setup. I will make a new connection. Now we need to connect to the ACC partition you should all have access to. And before I forget it, I will do the change in the tool train. I generally do the purge here because both partitions have defaults that sometimes you have to either manually remove or choose the GCC by default. For example, the GPP partition starts with Intel MPI because it's an Intel partition, Intel systems, and so on. It's not surprising, but for our case, we are using the also on this part the GCC version. We have also a different toolchain setup on the ACC partition for NVIDIA SDK. If you're making module avail on SCORP, you will find it and it will tell you which modules you need to load. But on the overview slide I have here set, that's also downloadable. There's also last slide, which basically shows the alternative toolchains we have for SCORP and Scalasca on the system. But for the hands-on, the GCC element is fine enough. And we are loading also QClip and so. Now we go to our hands-on folder. If you're were able to follow me so far, you also have downloaded the other example by default. So go to my user folder. Now here we have the tleaf CUDA. tleaf is an mini app. There's a set on GitHub from UK and Mac, which offer various tleaf variations and cloverleaf variations for different computing paradigms, which is nice if you have a tool to compare different versions to. And it's they're relatively easy to get to run and also to run with a limited amount of resources, so you can work with them. We also prepped this one relatively for our workshop here. Okay, text a bit. Looking at the makefile. This comes with a lot of text. At the end of the text, we basically have the compile line that's relevant for our example. And it's basically structured similar to what we use for this BTMZ. In this case, we make some choices about compiler, which are the MPI compiler, etc. And it's an Hopper NVIDIA architecture. And then we also do the similar to the BTMZ, we have a prep variable for the compile step with prefix of score P. In this case, since we want to make a CUDA instrumentation, we also set explicitly -- CUDA. In theory, there is a score P automatic recognition if a CUDA compiler is used, but there are certain cases where our heuristic doesn't work. So usually, if you know that you're compiling a CUDA code, please set the -- CUDA. It avoids some issues. Normally, we would do uninstrumented run like we did with the BTMZ, but this is already filtered, and besides, this CUDA code doesn't need that much filtering anyway. Plus, we have seen this for the BTMZ before, and the process is the same. You look at the Scopy score output, and the only difference is that you now have also CUDA paradigms listed with regions for the CUDA regions you will see in the output. But since you usually don't filter them, some you can, but most of them you don't. You will still basically filter first the user functions that you want to get rid of to reduce the trace size. But in this case, we don't have to do that because it's already limited to a set number of functions, and for time reasons. So this is the same as we saw before. We now see the prefix Scopy -- CUDA before every call. It doesn't matter if it's just compiling, in this case, F90 file. It doesn't hurt. It just enables on the Scopy side the CUDA instrumentation. And that's something to remember for a lot of these paradigms. You need to instrument it into the instrumented binary, so on the instrumentation step, and you have to set variables so that the instrumentation is used during runtime. So now we have a similarity to what we had before, a bin Scopy, and we have the T-leaf binary, which is now compiled with Scopy, and an input file that fits our needs. And we do copy from the job scripts folder from Nostrum 5. And now we are going directly to the, we can use the Scopy file. And for a simple profiling run, it's largely similar what the settings are. We are having, in this case, since there are 4 GPUs, we are using 4 GPUs per node. And since we only use one process per GPU, it's with 2 nodes, a total 8 tasks. There are some OpenMP threads, but they're not doing much. They're basically just used in initialization phase, but they're still in there. And then we run with similar settings. The new elements that we want to see here, we first enter at the Scopy filter file, and then we have set for CUDA some variables. The enable equals default. that's a set of standard options to implement. I will show a bit more about that in a minute. And we set a buffer size, which can be, you can most of the time leave it out. Setting it a bit larger doesn't hurt. The current default is a bit too small for efficient use. So setting it to something higher is doesn't hurt. And otherwise just the experiment directory, and we are running this out of the box. I was checking that the file is there that I referenced. I mentioned the config variable, and as I pointed you to the copy info command yesterday, now we can look at what the copy info output for the CUDA enable options are. Dash full to get the full information. And if you're looking for CUDA, you find the CUDA enable. And it's since this option is not a Boolean or a string or something like that, it's a bit set where you can choose an option or a set of options. And there are quite a few. We have host side options like runtime and driver. They're mostly complementary. So if you enable both, you most of the time get a runtime call, and for the same runtime call, the driver call. So you usually just want one of them. And then you can get to the GPU side where you can measure the kernels. If you activate the kernel call side, you're getting a link between the CUDA launch side on the host side and the instances it spawned, which we want to look at. And it helps organizing and bringing together the asynchronous execution inside of Cube. And you can get additional information. Currently, the default set of options is relatively complete, along with driver, kernel, some counters, the mem copies, idle. Idle is basically where the GPU doesn't compute anything. It's an artificial region. And this is the overview. And this works also for different GPU paradigms. You have an option that's an enable option with the paradigm, like ACC enable, and you get a set of features that you can select depending on what you want to measure. Measuring everything can get to a bit of information overflow, so scaling it down at some point might be relevant if you're going to, if you're starting to know what you want to look for. And since we are currently still waiting, another information that it's nice to get from the copy info command, in particular if you are using in Scopy installation on a system that you didn't install yourself, looking at the config summary is always an summary. That's basically the way it was configured. And while it may contain a lot of stuff that doesn't tell you anything, you find basically elements that are supported by this installation and are easy to identify as if you compile it as PARPI, if you have OpenCL support, if you have CUDA support, and which libraries were used. So if you find out that something is not working as expected, looking what actually the Scopy installation supports that you are working on is quite helpful. So now the keyleaf program ran through. And if you're looking at the output, the standard SCOP output, this is the T-leaf where it prints a lot of information during each step. But it also lists at the beginning the GPUs it used. And since we're using 2 nodes and in total 8 NVIDIA GPUs, we're basically seeing the list of the 8 GPUs it's used. And in the end, it ran with a wall clock of 41 seconds. Since we didn't run the reference version, you have to believe me, that's roughly the same time as the reference version. So now that we have this result, and it looks basically from the outside the same, since we have the square, then we can also remap this file. And just to show the scoring output of such a GPU measurement, now we also have categories, like I mentioned, like CUDA. So you're basically getting a category for different event sources. And yesterday we just saw the additional sources of MPI and OpenMP. And now we also see the CUDA, which does have a large amount of contribution to the total memory. And as I mentioned, there are only sporadic calls to some OpenMP, which doesn't really hurt in this context. So now we want to look at it in Cube. And I'm again using the app image. It should open at the same point it's opened last, so we are still in the BTMZ. Then we go down, and there we have our T-leaf CUDA. There's bin SCOP and the SCOP T-leaf. And again, the default name for the remapped one is the summary cubex. So we are getting similar effects. The looks like a summary of a standard profile. And if we are looking now at the system tree, which probably has the largest change, we also see the CUDA devices or GPU devices in general, but in this case CUDA. And the structure is that we have here our node. And below the node, we have one zero. Let's see. We can, this info, get some additional information. In this case, there are attributes that are used for this. I'm currently at a bit, I think our measurement ran on the same device and not 4 devices, at least. The PCI bus. We have our 4 contexts. We are seeing the linked to the depending rank. If we have our 4 ranks per process, and we can get from the link to the corresponding site, which is the process that created the CUDA context. So you see where they belong to, and we have exactly the same number of contexts as we have processes. What we should have or want to have is actually one device for every process, which we don't have. We are working on the same device, and we are using PCI information for identifying the device, and since they all have the same ID, similarly, the cube result shows them as the same device. So it's seems that we probably should be using an option to distribute the GPUs over different devices. Let's check the verb script. I'm not sure. Is there some form of script on the system to distribute the CUDA visible devices?
So if the application doesn't do it for itself, which I usually prefer that the application
should do, yeah,
the local GPUs, but if they don't, yes, there's a support team provide a wrapper.
Yeah, that's similar.
That basically iterates through local MPI ranks, and basically how it works is if you bind the process to a NUMA node, then you bind to a NUMA node, and you get you also put the CUDA visible devices to that specific GPU, and then you.
Yeah, as that sounds familiar. That's similar how we do it in Jülich. Right now, I think it's something which was integrated basically into Slurm itself, doing the same script. But originally, we also used a script which basically looked at the rank we are running and modified the. There's a CUDA variable called CUDA visible devices, where you by default it gets device 0 every time is the first one it takes, and if it just uses one, if a process just uses one device, in the end every process uses the same device. This was basically the reason which we actually added this PCI bus identification information, because before that point we couldn't actually see if we're running on the same devices or not. In this case, we can see, yes, in this case, we are all of the 4 processes running on the same device, which is fine for our run because we are not measuring the actual performance of it. But in your normal case, the most common use case is using one GPU per process, and either you have to specify this in your application itself, or using the script provided by the admins to set the visible devices to for each for each rank differently, or do something like arithmetic in your batch kit to set this depending on your rank. But this is an information you can get out of the measurement and check what your program actually ran on. So in this case, since we're running on the same device, we see the other information. In principle, one device can have multiple contexts, and in this case, each context is controlled by one of the ranks, and we can get the link to it. Since we measured with host side and kernels, then we get in the call tree, second root tree under the key leaf. And this is called kernels. This is an artificial root node so that we can organize our representation. Then we have basically a list of the devices. Of the kernels, and make a bit more visible. And these kernels come with certain GPU statistics that were added as parameters. It's not the best way to represent it, but since they are specific to the kernel instances, it was something we had to do. Present in the call tree and share this information. And we again have a link which then links to the call side of your the launch point of your kernel. which is linked to the specific CU launch kernel. That comes from the driver option, and you can jump from the launch kernel to the selection of the device instance that is used for this. If you have the same base kernel but different call site locations, we are getting some substructures here, which are just for organization since the lists get long. And we see the execution of the different kernels from different call sites or other parameter differences between these instances. If you're collapsing this for more, to get a bit of order in things. We are also now seeing additional information in the call tree. Since we are adding a new paradigm, we also have the time spent in CUDA overhead, and which is basically on the host side, we see something like, let's see, let's go down to in this case, we have launch kernel. We can general memory management. These are then the mem copies we can see, and the kernel launches. So our different instances of CUDA overhead can be separated. The probably interesting ones are something like the coder synchronization, which takes time, where the host side basically is waiting on the CUDA cons to complete and to return. These are our instances then of the device synchronize to measure these. And depending on the options, you get a different amount of the additional CUDA information or different other settings in the for different other GPU paradigms in the similar way, structured by paradigm, and then can look up in the information. You're also getting CUDA memory bytes that's from process metrics that transferred, and the additional allocated bytes, and we also get the transfer of bytes in the byte transfer metric. So this is basically what you're right now getting with Cube in these instances. For additional information for CUDA, as I mentioned, we have the principal structure of Cube, how we evaluate data from left to right over metric tree, call tree, and then system tree, is historically built around the symmetric nature of OpenMP, where you have basically one call path like a OpenMP parallel, and then on the system tree you see the different threads. The inconvenience of asynchronous threading or kernel executions is that you have a vast amount of new call paths in the call tree, where each of your threads behave differently. So you basically already putting information of the system tree side into the call tree because it's split up early. It's the same issue you have if you're running with p-threads, where each thread may do something completely different and has to be treated differently. So the selection is that was more complicated. And one of our challenges for the future is to improve the behavior of Cube in the asynchronous execution modes. So looking at the time, I will continue right now. Something I mentioned for Scalasca is that we are currently limited in what we can do with GPU programs, because on the technical side, Scalasca works on the same threads and processes as the application and does its own processing there. But that only really works in this one-to-one matching with standard CPU threading and not with GPU calculations with CPU streams. So at the moment, we cannot handle measurements that have locations that are not host threads. So if you want, but still want some information from the Scalasca side, we can do measurement. And I can show you what you can get out of it at the moment with what side effects you have to be considering. So if you're looking at the Mare Nostrum 5 Scalasca drop script, right now what we're doing here is basically, instead of using setting Scopy CUDA enable to default, we're setting it just to driver, which is one of the host side elements. And otherwise, we're running it similarly to the Scopy run, but just with the scan -t for tracing and the S run on it. And with this, we are adding the CUDA host side to the measurement of the Scalasca run. And we will see what we get out of it in the moment, depending on how fast the system is schedule speed. Just while we wait, I can show you on the left side. This CUDA enable is the option we right now used. You can specify singular options with comma separation, or just use the default one or one specific one you're specifically interested in. The same works for the other paradigms we use. We have Scopy HIP enable, we have Scopy OpenCL enable, which have all similar options, and you should look at them up in the Scopy info output. We have a special case with OpenACC. Since OpenACC is just host side, they don't have an own device side interface. But since they're implementing it underneath with something like CUDA, so if you're running on an NVIDIA device, you also can enable the CUDA adapter, at least for the kernel side. So you're getting a mix out of the OpenACC part and as well as the CUDA information. So now we are looking at this measurement. We are now doing the same as before. We are doing a square HS on the trace folder to remap it. So, and now let's see what we can get out of this in the trace folder. And now take the trace cubex. Okay, it takes a bit of time. So the basic question is, why should you use Scalasca analysis on CUDA code when it doesn't show you the kernels? It's a good question, and but the answer is the primary objective of Scalasca is the analysis of communication and synchronization behavior between inter-process and inter-node behavior. In particular, if you're looking at MPI, OpenMP, etc. And CUDA executions don't happen in a vacuum. So you, yes, you are interested to run, and for your CUDA code, you should be interested in running your CUDA code efficiently, but you also have to look at how the inter-process behavior looks like. And this is a situation where Scalasca can help you. You're getting the same critical path and delay and wait state analysis for MPI plus CUDA code. You're getting with a non-GPU code. So for the, but you have to be clear that your focus is the analysis of the MPI and other paradigm side of this code. Because if you're now looking at the code tree, you'll see that, okay, now we see only the host side of the measurement. And the interesting thing that you have to keep in mind when looking at critical paths and other times, that our computation time of our kernels basically now happens inside CUDA overhead, or is registered at CUDA overhead, because the time is because the CUDA host side calls that are waiting on the kernel completion are now getting attributed with the time that the kernel execution takes, because you see them just as waiting time, and you don't see the kernel execution actually on the GPU side. So if you're looking at the by example, we are now waiting in a CUDA memcopy. These are then also the interesting points on if you're looking at the system tree, you are seeing them usually in the master thread if you're running the CUDA out of the master thread in this case. And the time there is that's the relevant part, but you have to be aware that some of it is actually kernel execution time that should be positive computation time and not just overhead. And these parts are usually also then on the critical path where you are finding the CUDA codes, because the CUDA computation is relevant to the critical path. So yes, you have to keep in mind it's a workaround for the current state where you are with Scalasca. But since you still want to look at large MPI codes that also have CUDA, this is a solution that you can at the moment work with. We are trying to improve this. It's always a question of manpower and hours, but the problem basically is that Scalasca is as many of the tools are historically grown, and with the conception of purely host-side MPI, OpenMP basis, and growing beyond that is take time. So I think we leave for now the demo part and look at a bit more of the next slide sets, which are more presentation of over additional information. I want to present to get you an overview about other features you might want to look at, or if you're, in particular, if you're running your code, if you're running into an issue, okay, this might be a topic that can be addressed. Or this next slide set is basically a collection of topics that are addressed in the context of Scorpio measurements and areas, and we basically give you a 2-slide heads up. Okay, this is something how you can address this, get started on it, and if you have further questions, you can ask us now or in the follow-up after the workshop if you are running into similar options. It's also something, each topic could be a wider presentation, but it's also a lot of these topics are more specific and depending on your code, completely relevant or completely irrelevant. And so there is a bit of a collection style. So bear with me, and this is. So one example I think I shortly mentioned yesterday is that the context of build systems is sometimes problematic if you want to prefix a compiler command, depending how they're structured, what they respect in terms of compiler names. And so for one, we have the option that once the SCOP-P is configured, we're creating compiler wrappers for every compiler that is supported. So here on the slide, it's this Intel ICC. So instead of having SCOP-P dash and then the ICC as compiler, you can just use SCOP-P. Instead of the SCOP-P space ICC, we have a SCOP-P dash ICC command, which basically wraps the prefix, the options, and afterwards we just provide it with the command, the parameters. The advantage is, for example, in this case with CMake, you can define it as a singular compiler, which is instrumenting your application. The other advantage is you can set options like compile a SCOP-P wrapper off, so that, yes, you replace the compiler, but if you make a CMake, which basically tests a bunch of stuff, you don't want the tests to be instrumented. And often can you run into issues with it. So during the CMake step, you can deactivate the wrapping and just run it as ICC. And then in the make step, you run it without it, and you get SCOP-P ICC as an instrumented statement. You then also can additional parameters via environment variables to the compile step to get further on the path there. Next topic that we haven't mentioned so far is user instrumentation, which is quite useful. And in particular, if you know, have some idea about how your code is structured and what are the interesting portions of your code, you can basically mark regions that you want to see in the results specifically. For example, if you have a loop iteration that you want to see, you can specifically mark it and look at it then in the result file. It's also if you have problems with filtering, because there's so much stuff that you need to filter out, you can also deactivate compiler instrumentation completely and just rely on a handful of manual user instrumentation. You don't want to do complete replacement, but if you have half a dozen fun regions you want to look at, this is the way to go. And to enable them, you have to use -- user on the SCOP-P instrumentation command, and then they will be running. You have to, on the software, on the source code side, you have to add the include file. And for Fortran, you have to first make the declaration of a region, a name you choose, and then region begin and the region end. And you have some types if you want to identify a loop or just a dynamic region, that's fine, and give it a speaking name so that you can recognize it in your code later on, in your output later on. And we have the similar way for C++, that define the name and then begin end. The easiest is probably if you go directly for C++, but that just works for C++, where you can do just before for SCOP-P user even, and then with the solver and region type, and that's sufficient for C++. There's more variations on that, but it's quite useful. And since it's macro-based, and if you at some point included this user instrumentation file in your source code, you can run your code with and without user instrumentation. So you actually can leave it in there if you want, and just see the output when you want to measure something. Another point that is quite relevant is the control API, where you can stop recording and restarting at a later point with Scorpio recording off and on. For this the classic example is, for example, with the POP methodology, you want to choose a focus of analysis and actually measure only that analysis part. The classic example is you don't want the initialization phase of your code to show it up, or fill up your trace buffers just with something that you don't actually need. And so you can stop the recording and only start the recording again for the iteration phase, for example. It's also a way, if you have a use case that based on the input sizes required, simply runs for a certain length of time, too long of a time to measure in total, so that you can run the example on the required time, but just measure a short time of it. The important element here is that you have to be careful where to place the recording off and on. You usually want to do it on a process level, so not inside of a threaded region. And you have to record the beginning of the MPI init. So the first time you may put the recording off is after the MPI init, because then you have to get the initialization, otherwise you might miss something. And our measurement actually initializes on MPI init. So if you're missing that, that's not a good idea. And then you can turn the recording off and on for what you want. And for the end phase of finalization, you should turn it on again too. So just turn it off for specific reasons you don't want to see. And just as a side note on that, right now how it's working, it's primarily a function to reduce recorded events for tracing. It doesn't reduce really the overhead in time terms for the measurement, since it goes through a lot of steps internally that are the same, just it doesn't record the events. So it's a measure to reduce trace size and less important for profiling. The topic of counters I mentioned yesterday shortly. This is a few standard counters, but we have a few more options. I mentioned the Scorpio metric PAPI, which just puts where you put the name of the standard PAPI counters that you get by PAPI avail or PAPI native avail. But you can have all per process metrics like level 3 cache or something, and these create an own metric location, because they cannot be attributed to a specific location. They have to be an own location, have to be looked at separately. Additionally to PAPI, we also have perf counters from Linux, and they function technically the same on the Scorpio side as PAPI. We have you can put the names there. We have some per process metrics. And generally perf lists the counters. Additionally to that, we also have R usage counters, but they are less commonly used. And also we have a metric plugin interface where you write your own plugins, and on GitHub Scorpio there is a repository with some available plugins. Was more or less being kept up to date. Another topic is how to look at memory usage. This is also on a relatively high level, but we can set a variable Scorpio memory recording to true and a Scorpio MPI memory recording to true. And this will record additional metrics like maximum heap memory allocated. I can see where and on which process. And we get metrics about allocations, deallocation size, and basically calculating and tracking the information. And then if memory is allocated but not deallocated, then we get information about bytes leaked. This is basically intercepting all the malloc and deallocation and free calls that we get from the POSIX and calls, and also tracks the MPI memory allocations. The accelerators are basically covered. Here we see how Vampir looks at it's basically the timeline view is similar to what Paraver does, and you have basically for accelerators, you have your master thread, you have your CUDA thread, where right now we're getting mostly the kernel executions, and we're getting the transfer that where we don't have an endpoint directly, which is inconvenient at the moment, which also has some implications for the pop metric calculations at the moment. But you get basically the idea of where the GPU is running and where the device activities happen. And then you have on the master thread here, basically the stack of the running calls. You also then get the API calls inside from the CUDA API calls, inside the OpenMP directives, OpenSCC directives, which I mentioned when you stack basically OpenSCC and CUDA together. There's also a method of sampling for SCOP. It's not our priority first choice of use, but in some cases, in particular, if you have high overhead with instrumentation, going with sampling models is helpful. What should be mentioned here is sampling only replaces the compiler instrumentation, which is most of the time, not always, but most of the time, the main cause of the overhead in your instrumentation. So you're going with this --no compiler. And then we're running basically in a hybrid models where we still intercept MPI, OpenMP, and other paradigms, but then sample the information that we are getting from the sampling, from the user code, basically, and going via unwind to see getting where we are in the call tree. The reason why we don't sample the MPI calls is that in particular for something like Scalasca, we need every MPI send, this is a fitting MPI receive. And with sampling, depending on your sample rate, you can get unlucky and you're missing important calls, which is not necessarily, particularly if they're short, which is not necessarily a problem if you're just looking at the statistic of the whole issue. But if you're matching specific calls, you don't want to do that. And therefore, our sampling mode is a kind of a hybrid mode between instrumentation and tracing, instrumentation and sampling. Another part is instrumenting calls to third-party libraries. SCOP usually doesn't record calls to non-instrumented external libraries. For the first part, because we are just instrumenting that, what we are actually compiling. So anything that you're calling externally, you don't get. But it's also on a principal level, you usually do not want to see all what and instrument and generate overhead for everything that is not really in the hand of the user. Most of the time, you want to limit your instrumentation and the information that you're showing to the information that is available to the user and which he can change. So that is limiting to the actual code compiled. But on the other hand, you usually also want to know if something happens externally and which doesn't happen on its own. And for this, we have an instrumentation wrapping for external libraries where you can wrap basically the headers of libraries and see them as calls in the call tree and can attribute time to these. So we would not instrument the actual libraries, but just the headers. This is a process that has to be done it's a semi-manual step where you have to go through the library, create some example applications that checks the different calls, and then you have to check that you can actually build with it. It's a step that has to be done once, but then can be reused. And what you then see in your application is that you have a call to some MKL code or something. This is quite helpful if you are extensively using external tools, and that provides structure to actual codes and to actually understand what you are doing on your own side. So, we also have additional information for file I/O that we can, in particular, if you're going for MPI I/O, MPI file open, but also ISO and POSIX with fopen and open, that we can intercept and then display based on information that we get from the system tree. It's depending on how your application is running, it's a high level of data and can increase your trace data dramatically. And it's not necessarily something that you want to do every time. But if you're looking for something specific, that's quite useful. Sorry. I'm not going faster more in the details because I have to have to keep an eye on the time. It's something if you are looking heavily into I/O for your code, this is something you might want to look at, in particular if you're using something like API file I/O, where you want to see the results of that. Another topic that comes up more often in these days is Python. In particular, if you're using Python in combination with something like C libraries, where you have compiled C codes for the actual algorithmic stuff, but using Python basically as a workflow structure, which is quite common. And we have Python bindings for Scorpy that you can install via pip. And then basically you can execute as a module via -m Scorpy. And after that, it functions very similar to the standard Scorpy execution. You export your Scorpy environment variables like experiment directory, filtering file, and just add the option of the Scorpy to the execution of the Python script. There are additional options similar to the options that we have for general Scorpy executions, like using threading pthread --thread like pthread, using --mpp for multi-process processing, for MPI or --CUDA and --ship to see these additional options also in your execution. Important part also for Python, the same as for general user instrumentation, is being selective with instrumentation. So you can use import Scorpy and then via decorator or context enable, disable the instrumenter, and basically have if you have something like where you have an initial phase you want to deactivate it for, and just for the actual algorithmic iteration phase you want to actually add the instrumentation to it. Disabling is generally also useful for input of modules, general uninteresting functions. and functions that basically reduce the overhead. It's the general principle we are using for instrumenting and filtering in general. Also, you do similar to what the no compiler does for the remaining is no instrumenter, selective enabling of functions, and where you then have something like with Scopy instrumenter enable a specific calculation call. In particular, you have to be careful with Python, because if you instrument everything in Python, you get very deep hierarchies often, in particular if the classical type of Python use with frameworks and such, where you get multiple level of abstractions. Until you really see the interesting parts you want to analyze, you have to be careful not to see too much Python boilerplate that you don't actually want to see. So the effort of reducing the measurement to something that you want to see is notable, but worthwhile. This was an example with an hands-on that we are not doing. But as mentioned there, if you're going to Python MPI, you have to specify the -MPP and this MPI. But otherwise, then you're running the same, the srun with the number of processes and just the additional parameter. You have to be a bit of careful with mprobe and memreceives, which are something that's default for MPI for Pi. So you disable the usage. There's an export for that MPI for Pi probe. There are some MPI functions that can be very problematic, like probing, like testing. If they run millions of times until they're successful, they can generate very large traces and very large overhead. And if some libraries have a default behavior that's along those lines, this is something to avoid. Yes, mentioned in principle, the CUDA and HIP instrumentation is the same as for the standard C, Fortran, and etc. Instrumentation. You set the environment variables. You mention the --CUDA and -HIP accordingly, and make sure that the buffer sizes are large enough and increase if necessary. If you're running into buffer problems with Scopy, you're generally getting a message that you should increase in buffer so and so to a necessary value. And in particular with buffer flushes from tracing, you want to avoid them at all costs, because they are disturbing your measurement to a hefty degree. Okay, this is basically this summary for this information, and we are getting back to our standard slide of how to contact us, which is particularly important for this one, because this is such a collection of different topics that you might run into at some point. Take it away as a reference document where you can see, okay, this is something I want to address now, and if you have questions, you can get back to us, and we can try to help you and connect you probably also to the one which the most experienced with one of these topics to get to the best results for your site. Today, for me at least, we are wanting to make a short look at Vampir. Let's see. So Vampir is a trace visualization tool based on time intervals and statistics, and it's developed in Dresden and the university, or technically an offshoot of the university. and it's a commercial tool which can work with OTF2 traces. Since we have no one from Dresden here, and also we don't have Vampir here on site. It's just a presentation without actual hands-on, even if it's on the slide set that I really use here, because it's just an overview over the toolset. In its classification, it is in a similar space where Paraver resides, working on traces, in this case on OTF2 traces, and we want to get a basic overview over it. So it's basically as an alternative and a supplement to the automatic trace analysis with Scalasca. So to show you the timeline, the dynamic runtime behavior graphically at any level of detail, and then provide additional statistics and performance metrics. You get timeline charts, which are basically the default view, and show application activities and communication along these time axes. But also you have summary charts that are based on the current interval shown that you have, and provides additional information. On the technical level, you can, if you install it just on your system or on your client, run your local Vampir via the command Vampir, and it's a thread level parallel system application, and can then run on the trace files that are of small to medium size to run basically comfortable on this setup. If you're getting into huge Scorpy traces that are very large, then you generally want to leave them on the server and run a Vampir server as a backend to Vampir, and which can run on, as a drop on multiple nodes to handle the trace sizes, and then connect to the Vampir client, and which again runs then locally on your system usually, and connects via network to this Vampir server. Yeah, this is the starting options that you don't need to look at right now. You usually have to account for that the system runs, this Vampir server doesn't run on the login nodes, but on a compute session, and you have to make sure that you actually can access the Vampir server from the outside. So that's a bit of technical issue that you have to clear. But once it's set up for your system, that's not that much of an issue. Right now, we want to look at a bit of the features of Vampir in an example from an BDMZ trace. So if you default OMS, you get a view like this. And at the top, you have the total runtime with a very high level abstracted view of what you see in the main view. And the main view shows by default the whole runtime, but on the horizontal axis and on the y-axis, you basically have your structure between ranks and threads or locations, where also in a CUDA program, the CUDA locations would hang. And all the regions are basically color-coded by default color selection. That's usually by certain categories like OMP, MPI, user code. But you can also distribute different color codes. You get downside here the function legend, which is the default distribution basically. Depending on your use case, you tend to end up color coding for the specific information that you want to actually use it for. Yeah, in the main timeline, you get basically detailed functions about communications. The black points that you see communication points and communication lines, and then you have the coordination points that you can see as patterns behavior in the output of the collection. You can scale it up and down in both axes, and it will try to visualize all of it in one screen. As additional information, you can get for example, function calls as a stacked bar chart for every info for individual process or location. You can select the process, and then you see what the current call stack is at each point in the time for this, how deep it goes. Similarly, as with Paraver, you can identify easily time phases, so you can see in the structure what is the initialization phase and then the computation phase, and then you want to usually zoom in on some of the computation phase, and if it's iterative, also on a selection of iterations. The nice thing about the measured counter to be shown before, you can get the counter as additional timeline elements that fit to the current scale of the timeline and get a detailed amount about the information that is provided by a counter trace. But you don't have to just use the number as given by the recorded counters, but you also can run metrics on this. There have some default calculated ones, but you can also formulate new metrics that are based on existing counters and combine it with time and visits, and count something like page counts over time, and see, depending on where you are, use these count information for more detailed analysis elements. For example, you can get also, here you see an example where you have the communication patterns between different processes and ranks. If you're on a very high level of zoom, you only see the dots, but if you once you zoom in, you generally see the communication lines between the different communication patterns. You can show if you select a certain function, can get more detailed information about that function. In this case, they used initialize, and what type of function is, how long this interval is, and the duration of it. If you're have a large example with a lot of functions, you can easily use a search function to find the respective functions and highlight them. And then, since every additional information bar is generally stacked, synchronized to the above one, you can see that in this case, the page faults align with the specific initialization functions and can localize where they're actually happening. In this example, we see additional values for calculate metric of basically higher number of floating point operations, and we specifically see that, okay, the initialization phase, there's not much happening, but afterwards in the computation phase, we are getting the specific information. So it's basically using the counters and matching them to the location where you are in your Vampir output, and synchronizing the views automatically so that you see where you are in your view. The similar behavior you can, for example, observe here is an example where you have multiple communications. You see the communication lines, but you also see that it's basically the API communications is happening in between OM and P loops. And on the counter side, you see that the floating point operations for these communication times, so your waiting times, etc., go way down, and this is expected behavior, and you can align these counter information with the behavior of the application. When we are, for example, talking about the patterns we saw in Scalasca, and in this case, we basically have an example of an early reduce where some processes are already early in the reduce situation and are basically waiting in MPI. for the remaining processes to enter the reduce. And we see that the difference is notable between the process, at least at this level of zoom. And we see this behavior not just in the timeline as time, basically the white areas are where there's nothing happening, where the OpenMP is nothing doing nothing. And then you also see this reflected in the counter display, where the floating point operations go down in the waiting time for the processes that already entered the reduce and are waiting for the remaining processes to continue. You also can split information by on a profiling information, basically calculated for a specific time span, and accumulate it over this area and get information how much time you spend in certain areas for a specific code. In this case, we are using the OpenMP do loops that are the main elements of computation for the BTMZ. And you look at this on a whole level or on a process level. This top one is the aggregated over all processes, but you can also look at it as a bar chart basically for per rank level. So this is the amount of time each process spends in each elements. And if you hope, if you want to generally probably similar behavior, otherwise you are running into imbalances at any one at some point. If you're you can also, instead of looking at all the processes in one go, you can group processes that have similar behavior and try to distinguish behavior based on which processes are grouped together, which have similar behavior versus others that have different, and see if the alignment has impact on your execution behavior. Yeah, this is basically the very high level overview of Vampir. If you are interested into more details, I recommend contacting us or the people from Dresden. And in principle, it's a scalable visualization of event traces, particularly with the Vampir server behind it. You can look at really large traces. And it works as most of the other tools we have seen so far with color coding to easily identify program structure based on elements that we can recognize. And it supports multiple trace formats. Although for our use case, it's generally OTF2, but there are also other trace formats that are used from different contexts, less from not just from HPC context. Yeah, and that's the last slide from me today. And I want to thank you for your attention. And if you have questions, I will try to answer them also to Vampir. But if you have questions for everything else, feel free.